Hey, and welcome back to the Structural Engineering Podcast. I'm Zach.
And I'm Max.
Max, what do we talk about this week?
So this week we talked with Ron Klemenczyk about a lot of things. It was a pretty wide-ranging conversation, hitting on AI, performance-based design, like everything that is hitting the field right now, the changes that we've seen through this. So Ron is later part of career and we are younger. The window that we've seen, where we are going.
One thing really I found super interesting was our discussion on speed core. And in my mind and within my career, I thought it was something developed, probably in the last 10, 15 years. But knowing that he and others started this discussion before the 2000s, mind-boggling.
Putting a scale to all this is pretty valuable.
And what it took to get here. And I don't know, there's so much fun insight and discussion around his career. And, even like the beginning part of our discussion where he was asking us silly questions about rap artists. And Ron is such a fun character within structural engineering. I've found Max since that episode and even leading up to it, talking to other people in the industry about Ron was pretty fascinating and awesome. And how much he and MKA really have influenced the industry.
It was a fun time. So I hope everyone really enjoys it and reach out with any questions and usual.
Let's get into it.
The Structural Engineering Podcast.
Ron, welcome to the Structural Engineering Podcast, where Max and I are both super excited to have you on.
Happy to be here.
To start us off, would you mind giving us a brief introduction of yourself and kind of about your career a little bit?
Oh goodness, how far back do you want me to go? I'll do this in our company. We occasionally, I have meetings, regular meetings actually, monthly meetings with our young staff, new hires, interns, etc. And the first thing we do as the icebreaker is we go around the room and you have to tell your entire life story in 2 minutes or less. And so I'll do that. How's that?
That sounds great.
So I was born in Racine, Wisconsin. Very famous for the S.C. Johnson and Company Frank Lloyd Wright headquarters building. And I thought when I was a kid growing up, that was the coolest building on the planet Earth. So that was influential in my life. I ended up going to Purdue University in West Lafayette, Indiana for my undergrad. Graduated there in 1985. Went on to Berkeley for my graduate studies, master's degree from Berkeley in 86. Then I got a job in the Bay Area and I worked for a small consulting firm called Robinson Meyer Julie Associates, which I don't think exists anymore. But then I worked there for several years. If I'm very transparent and telling the absolute truth, I chased a girl to Seattle and the Seattle worked out, but the girl didn't. So I found myself in Seattle working for KPFF, and I worked for KPFF for about 5 years or so, I think. And then in 1992, I joined Skilling, Ward, Magnuson, Berkshire. And so I've been here now at SWMB, now MKA, since 1992. Here we are, 2026. So that's 34 years of pure joy.
That is amazing.
Well, that's my life story in 2 minutes or less.
I like that a lot. Man, what a fascinating, starting in Wisconsin down to the West Coast and then up the West Coast.
Yeah, when I was a kid, kind of going off that riff a little bit, a lot of my dad's side of the family were in the Chicagoland area. And we would go down occasionally to visit aunts and uncles and what have you. And on some of those trips, my dad would take me into the city. And at the time, they were building the Sears Tower. And I thought the Sears Tower was incomprehensible to me as I don't know, maybe I was in 5th grade or 4th grade or something. And again, that was highly impactful on me, thinking, I want to do that. That's so cool. I want to work on stuff like that. So from that age, maybe even younger than that, I started thinking I wanted to build buildings. And then when I was a senior in high school, I had a math teacher who helped me understand how you could explain many things in the world with math. And I thought that was super cool too. You can explain all kinds of things, everything from the trajectory of a baseball to, spaceship orbits to statics and dynamics and you name it. You can do it all with math. And I thought that was cool. So anyways, I ended up in engineering school. So there you go.
This episode is brought to you by CalcBook.
If you've ever spent hours digging through spreadsheets for errors or used software that spits out results but hides the math, you've probably thought, there's got to be a better way.
CalcBook gives structural engineers transparent, line-by-line calculations in a clean, user-friendly interface, so you can trust your results and work more efficiently.
Listeners of the Structural Engineering Podcast get 50% off their first 3 months at calcbook.com with promo code SEPOD. That's SEPOD, all capital, all separate letters. We'll put it in the show notes.
CalcBook, calculations done right.
Did you
So no
start
background with
architecture?
the family.
I think of a young child, see this building, it is designed by
Yeah, yeah.
is the kind of commonplace way to say this.
Yeah, I thought I wanted to be an architect until I was in about middle school. I have 2 uncles who are both civil engineers. And in about middle school, they sat me down and explained to me what an architect did, what an engineer did, what the contractor did, kind of explained how the world turned. And it was pretty enlightening and also very clear that my brain was wired to be more on the engineering track than on the architecture track. So that launched me into the whole engineering direction. So yeah, I'm kind of a freak of nature in that way. You know, how many kids when they're like in junior high know what they want to do for their career?
Yeah.
Yeah, most my kids, I got 3 kids, and most of them didn't know what they wanted to do with their career until they were graduated college. And even after that, one of them is on his 3rd career already, my son. And he graduated college thinking he was going to do one thing, and he didn't like that. So then he did another thing, and he didn't like that. Now he's found something that he truly loves. And it has nothing to do with what he's studying in school.
Yeah. I didn't realize architecture was a bad idea until I was 2 years into it, 20 years ago. And
Yeah,
that
no,
was
it's-
more complicated, but I made it here.
Yeah, architecture is a good thing. Don't get me
It's
wrong, Matt. I got honorary AIA next to my name. So, I totally respect architecture. It's
Yeah.
just I know that that's not my skill set and my strong suit. I can pretend like I want to be an architect, but then, revert back to, I'm more the pragmatic figuring it out, how to do it.
I get my Dwell magazine. That's as much architecture
Yeah.
as I.
Yeah, fair enough.
Yeah.
I think so often, the structural engineer is the architect's engineer, not necessarily the mechanical or electrical or civil, but we have to work so well with them to produce, successful, exciting looking buildings.
Yeah, the best experiences I've had, the most, shall we say, fulfilling experiences I've had have been collaborating with architects and other design professionals who have a respect and a curiosity for what the other technical specialists do, and vice versa. So, like, I dabble with architecture and mechanical engineering as well as structural engineering, and I'm happy when the architects or the MEP engineers do the same, when they dabble with structural engineering, and we're all trying to understand each other's view and thought process and, really work to complement each other in a hugely respectful way. That's the most fun. The least fun is when you I see this all too often, and I hear architects complain about this a lot, that the engineer wants to know when the design is frozen so that they can run their ETABS model. That drives me crazy, and that drives a lot of my architect friends nuts so as well. So that's not a collaboration, that's a food processing truck.
Yeah. Well, today on the episode, we're hoping to use and really talk about all of the experience that you've developed over your career from San Francisco through Seattle, KPFF to now MKA. And a place we wanted to start is talking about innovation. Something that we see you write about, something that's, really a huge thought leader in so many different, realms, from speed core to performance-based design methodologies. So I wanted to start off with a question for you of why is innovation difficult in structural engineering?
Yeah. Well, how long do you have? The list is very long. I'd say primarily it is just momentum and human nature resistance to change. That there's, and it's not just structural engineering, it's in the whole building sector. Contractors even being more stuck in their ways than engineers. But there's just so much, uh, I don't know, built-in momentum to comply. And in fact, I'm going to go off on a tangent just for a second, but a couple of university lectures I've given recently, some of the faculty have asked me this question, how can we improve our curriculum? How can we better prepare the students to go into practice? And my response of recent has been, don't teach the code, because I'm not looking to hire compliance officers. Teach first principles, teach mechanics, teach strength of materials, teach concepts, have them do hand calculations. So when they come to us, they're actually somewhat useful, and we'll teach them the code.
Yeah.
And so that's a little bit off on a tangent, but it speaks to this, where is this kind of resistance to change and resistance to innovation, where is that seed planted? I think it's planted in some regards in how we're educated. And a lot of the education these days is focused on code compliance, which is really sad, actually. So it starts there and then it just builds. And like I said, contractors in particular are notorious for not wanting to do anything new and different. And with respect, they're trying to make a buck too, and they know how to build certain things and make money doing that. And so that's what they want to build, because then they know how to make money. As soon as they're asked to build something that they don't know how to build, then everything's in question. So that's where a lot of the resistance comes from. It's just, if you keep it all the same as it always was, then you have a chance to make some money.
Some internet issues, but I can repeat myself. I think our industry has a lot of anchors to the way we've worked for a long time. Even when we're trying something new, we need to be certain it's correct, right? What pushes innovation in an industry that's risk-averse, even when that's for good reasons? But how do we continue moving forward?
Yeah, I mean, what pushes it, well, for me, I just talk personally, what pushes it for me, and that's just never being satisfied. Never being satisfied. It's like playing golf, right? You can't win golf. You can only get better. Yeah. You can only try and improve. I look at that with engineering. That's why they call it an engineering practice. And it's because we're practicing all the time and we're always trying to get better. And that's really ingrained in me that I'm, at MKA, one of our company mottos, slogans, whatever it is, always striving for better. And we work on lots of cool things and we do lots of innovative things. And then we're never satisfied. It's like, okay, well, that was lovely. And we learned a few things. Let's do it different, better the next time. And keep pushing down that avenue. And as I go around the country and lecture, I made a presentation recently to the Structural Engineers Association of Arizona at their annual meeting. And I challenged them all to say, look, every day that you go to work, there's a chance for you to do something new and different. And don't set the bar so high like, oh, geez, I need to invent the next iPhone. No, 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 no. Do something simple, and challenge yourself to do something different, new, better. Start small and keep your eyes open. And before you know it, you're going to stumble across something, as that's what happens to me. I just trip over something and I go, oh, that's a chance to make it different, better. The other place that I mentioned to this same group, and I state often to colleagues, is if you want to find an opportunity to do different, better, ask the contractor who's building your current design what they like least. What gives you the most grief? What do you hate about my design? And contractors generally are pretty outspoken.
Oh yeah.
And they'll tell you. And that to me is the bullseye, right? If the contractor's complaining about something in your design, that's the bullseye for thinking about how to do it different, better next time.
Yeah.
And there's a whole slew of things over the years that we have gotten exactly that feedback, took it on board, and then proceeded forward to do it different, better next time. So
I have a broad question here, but thinking about when I moved to Utah, well, the first time, my house was built in 1907 or something very old. It looks the same as my house in Colorado that was built in 1980 when I lived there. I don't have multiple houses. Anyway, there's a side, tall buildings where we are pushing this industry and you are really leading that. But from the scale of this, do you think in 50 years, our houses will be built differently? Like what level of change might we see as the goal? Hard to put a scale to, but if we're, all we change is the 2x4 is now 3.5 inches, and many other little things, but you know what I mean?
Yeah. I guess sadly, that maybe is not the right adjective. I don't think there'll be a fundamental change there in terms of, personal residence construction.
Yeah.
And so oftentimes I ask myself when these kinds of questions come up, it's like, well, what's the forcing function? What's going to cause that to change? And I don't believe it's, somebody invented some new technology. And no, because that's a solution looking for a problem, right? Where's the problem? And there isn't really a problem, really. Houses are made out of wood, which is a sustainable material. We're all talking about sustainability. We're all talking about mass timber. So what I do see as something that could be impactful, likely will be impactful, is the growing labor shortage, in particular in the construction trades. How that's going to change construction processes, I think we'll see in our lifetime, because there just aren't enough people to do what needs to be done. So this is where robotics are going to come into play. This is where prefabrication, modularization, all of these things will gain more momentum out of necessity. That's the forcing function, is the labor shortage. And so it's already happening. But I think there's going to be momentum that accelerates there. And so I'm keen to kind of follow that trajectory and maybe not be so dreamy and more pragmatic about it instead, and think about, well, okay, how do I leverage that? So I'll give you a silly example. In the construction world, there's a whole bunch of advancements already being made with regards to autonomous things, right? But the one that just still fascinates me to no end is I look out my window and here in Seattle, and I can probably see, I don't know, 10 tower cranes. And every last one of those tower cranes has some dude sitting up there in a little glass box. And I'm like, we got people sitting in Oklahoma flying drones in Afghanistan, blowing up things.
Yeah.
Why do we got a guy sitting in a glass box 300 feet in the air with no potty, and he's got to bring his lunchbox up there? And why doesn't he sit in the construction trailer where it's much safer?
Yeah.
With a joystick and a bunch of video, cameras, and run the crane from the ground?
Yeah.
I mean, that's like a simple one. Apparently, there's a guy in Israel who has figured this out. There is some technology that can do exactly that. I researched a little bit. Anyway, my point being here is on the construction implementation of building buildings, including single-family homes, I think there's going to be some automation that comes into play, much more so than before.
Yeah.
Yeah.
I've been seeing like the large scale 3D printing in the concrete space. Great for, foundation laying. Formwork is a lot of time. A large device. It seems easier.
Right. Yeah. And not only that, but then the 24/7 possibility of that automated construction.
Oh, yeah.
Whether it's printing or, the one that I point at commonly is there's already companies that will offer you excavation of anything autonomous with autonomous backhoes. They'll come in and do the programming, and they'll dig your hole, whatever hole you need, with no people.
I can see my head.
Yeah. And then they can run it 24/7, provided there's no, sound restrictions or anything. But from a purely operational point of view, you can go 24/7 because there's no people involved, and so you can proceed much, much faster as well.
When it comes to innovation, I think people often, jump to risk. We've kind of talked about that, and which is then fearful, and lawyers and money and maybe some ego there too. You guys talk about innovation and taking on new things or changing the way you've done your designs or new technology. How do you guys mitigate that risk to feel more confident in what you're doing?
Yeah, well, we do our homework for sure. And these days, much more so than our forefathers. Our forefathers took a lot of risks, and they just winged it, and they didn't have all of the approvals processes and all the, things that they had to demonstrate to the authorities and this and that. They just did stuff. And they proved it to themselves, and then they went and did it. These days, we need to prove to a wider constituency, of course, whether it's the building official or the client's peer reviewer or whomever, right? There's a larger constituency that we need to defend our designs and our innovations amongst. And that's fine. I think that's healthy. It does slow things down a little bit, but it is healthy if everyone's participating in a, shall we say, positive way. So I'm all for the kind of collegial review, third-party review stuff. That's all good. But I just think that anyway, where were we going with this? I got off on the third-party review thing. What was your question?
How MKA manages risk?
How do we
when innovating?
Yeah, so all right, so I'm going to put a weird spin on this, right? But this is unique to MKA, I suppose. I view our greater risk as not innovating. And that's the innovation is how we remain relevant. And if we're not thinking about the next thing and how to do it different, better, we lose our competitive advantage. And to some degrees, we even go so far as lose our relevancy, meaning how can we be who we are and charge what we charge and, get hired to what we do if we're just selling the same stuff everyone else is selling, which is, code compliant ETABS design. So that's not what we do. So anyway, it starts with a philosophy of failing to innovate is the bigger risk.
Yeah.
Once we go down that path of we're going to challenge everything and think about everything and push and pull, then we just got to do our homework and do it thoughtfully, do it properly, and not be afraid of, and in fact, invite our competitors to the party and have them comment and review and collaborate on making it different, better. And that's when it's been most successful. So.
Yeah. If you were talking to a younger someone, maybe in college, just graduated, and what separates, an innovative engineer from the conventional, I think, especially at college level, that's when you need to be making these educational decisions and how you perform actions.
Yeah. The word that pops straight in my brain right away is curiosity. Is being curious and always wanting to understand why, There's a lot of commercials or things you've seen on TV. I remember, I think it was a Charles Schwab commercial a number of years ago, and the father and son are walking down the street together, and the kid, who's like a little kid, keeps asking his dad, why? And the father's trying to explain, Anyway, the long story short of that is that kind of childlike curiosity and the enthusiasm for learning, that's really the fuel that really can take you places with being innovative. If you're just, checking boxes and hoping that you get a paycheck at the end of the day, that's not going to really get you far. But if you're curious, Yeah. In fact, I was talking with just one of my colleagues here, a young person in the office just the other day, and they were asking me, what can they do to grow and improve their career trajectory? And I encourage them the same way as I do many. Be a student of buildings, in particular, those kinds of buildings you're interested in. Learn everything you can about them, not just the ones we do, but the ones everybody else is doing too. When I was young, of course, I read about these things in the magazines, in the newspaper, in trade publications, what have you. Today, it's all on the internet. Go mine the internet. This particular individual wants to design performing arts centers, music venues, things where there's live performance. Cool. I'm glad you're focused. You know what you're interested in. So what you should do is know everything there is to know, everything that's ever been published about every performing arts center that exists on the planet Earth. Make that your goal. And now you're good. So now you know something that people will want to hear, not just about MKA's projects, but about all those other amazing projects that are out there too.
Yeah, that I can. We heard that when we interviewed your colleague Travis on kind of the different venues and stuff that he works on, and it was a big thing. He kept bringing up sight lines, and we just need to make sure that everyone can see the stage or what's happening. And Max and I were both like, well, that's kind of on the architect, right? You just they'll lay it out. You then put the structure in, and then he went to vibrations and human comfort and said, these are the things that drive really good venues. These are that connected with me right now is like, man, that is exactly where Travis was coming from when he talked about all those things. That makes a lot of sense.
I'm glad to hear that Travis drank the Kool-Aid.
Yeah.
But yeah, I mean, we promote the idea of, we're not just structural engineers, we're building design collaborators. And to know about all these other things that are impactful to a particular building type, whether it's what Travis was talking about in performance venues, or whether you're into hospitals and you need to know about all of the various MRI machines and, or you're in laboratories or convention centers or sports stadiums, what have you, to know things not just about how big does a beam need to be, but why does the beam need to be there in the first place? Let's start there.
Yeah.
And kind of understand it in context and what's driving the design, and then contribute to that. That's a good thing.
I remember a Peter Rice documentary that I watched a long time ago, but he's designed amazing buildings, and one part of this documentary was this performance space that was exterior. There were no walls. It was just the art and supporting of this art and the platforms, and it was just he was so involved with the space that they are creating. It really was something that engineers should aspire to. I don't know.
Yeah, for sure.
The Full Moon Theater, if anyone wants to take a look at this.
In the end of the day, that's what we're doing, right? Is creating these amazing places for people to experience and enjoy.
Yeah. Would you mind walking us through a little bit so Max and I met you at the Steel Conference, and you were talking about speed core and bolted connections. Can you walk us through a little bit of the innovation? Where did that came from? Maybe a question from the contractor of how can we do our jobs better, and kind of walk us through the story of speed core a little bit.
Yeah, so I'm going to abbreviate it a little bit because I could start this story in about 1958, but I won't. And so I'm going to fast forward to about 2005, and I'm going to skip all of that part. We can have a whole nother podcast about what came before 2005. It's like, the Star Wars episodes, right? You get the one episode, but then you got to have the episodes so there's starting from the 50s until 2005. We're skipping that whole part. So in 2005-ish, what prompted it all was just, again, always striving for better, looking at the fact that not just we, MKA, but we, the construction industry, we're building all around the world these buildings with reinforced concrete cores and steel floor framing, and noting that the cycle time on the core was about half the rate of the cycle time on the steel erection, and that was driving the schedule. And so the question was posed, well, how do we do that different better? how do we go faster and eliminate that kind of drag on the schedule between the concrete cycle time and the steel cycle time. And that's kind of what hatched the idea of SpeedCore was we need to go at the rate of steel construction, but yet we need the stiffness and strength, mostly the stiffness of the reinforced concrete structure. How do we do that? Anyway, that's kind of where it came from. And then around 2005 or so is when we launched the very first formal kind of research project and trajectory at Purdue with Professor Bowman and Professor Krager. And now we've been in the lab for 20 years doing stuff to improve it and make it better. And, we really started in earnest probably in the maybe 2015. So we did about 10 years of diddling around, let's call it. And we didn't have a client. We didn't have a project. We had an idea. We had some money. Let's go figure this out. And we messed around in the lab for almost 10 years before we finally found a client who wanted to build a building with that system. So that was around 2015-ish. Yeah, about 2015. And then we did it. And now we're doing it again and again and again. So we're building number 3 right now, but building number 4, building number 5, and actually up to about building number 10 is on the boards. So there's a lot of momentum building now, finally. But it's taken 20 years to get there. A lot of people go, oh, SpeedCore is brand new. No, dude, I've been working on this for 20 years. So, yeah.
Sorry, Jason is SpeedCore, SpeedFloor. These are all performance-based design style concepts. Do you think that helps unlock innovation in a sequence?
Yeah, well, not oddly. In fact, I was just doing it this morning. There is a provision in the ASCE 7 code, and it's actually in the IBC as well, the alternative means and methods provision, that basically says you can do whatever you want to do as long as you can prove it works.
My favorite one.
And so the story is, to the building official, to the client, our design is 100% code compliant, because we're walking through this door right here that says we can do whatever we want to do so long as we prove that it complies with the intent of the code. So we don't need to follow the prescriptive language and check all these boxes on, redundancy factors and R factors and omega zeros and all that. We throw all that in the garbage can and say, no, first principles, alternative methods, we're compliant with the code through this door. And that unlocks everything, anything, basically. You can do whatever you want as long as you prove it. Well, it's kind of math and physics and engineering. So
first SpeedCore was Rainier Square Tower, the first project.
Mm-hmm.
So you guys developed this new system. It was in the lab for a while. And then you said, you know what? Let's just do a tower for the first time.
Yeah, that was a interesting story there. Yeah, normally you wouldn't walk out of the lab and then do a 60-story tower, but that's what we did. But the story that I'll share there is that we originally designed Rainier Square with a reinforced concrete core and steel floor framing, kind of normal. And we advanced that design through, I think, schematic design. The contractor, who was Lease Crutcher Lewis, priced that design, put a schedule together for that design, shared it with the client, and the client said, that's lovely, it costs too much and takes too long, stop. And so we stopped, and we put it in the drawer, and it sat in the drawer for a couple of years. And one day the client called up and said, well, I signed a tenant who's leasing the entire building, but it still costs too much and takes too long. What else do you got? Because I don't want that.
Wow.
And that's when we pulled SpeedCore out and showed it to the client and said, well, we've got this other idea that we've been working on for 10 years. And we think it'll work, and we think it'll save a bunch of money and a bunch of time, but nobody's ever done it before. What do you think? And, on the one side of the story, you say, well, the client was courageous enough and trusted us enough to allow us to do it. And the other way to spin that story was the client was desperate enough and had no other alternative. You decide which version of the story you
Either way,
want
the
to.
forcing function was great on that, right? It's like
Yeah, there was a forcing.
and yeah, it just
There
yeah,
was a
fine.
forcing function. And the good news is, the client is a client that we have worked with for decades, and the contractor we've worked with for decades. The whole team had been together for a long time, so there was a lot of inherent trust already built in. And so, the view of the client was, if anybody can figure it out, it's you guys, go figure it out.
This episode is brought to you by CalcBook.
As engineers, we all want calculations we can trust, but spreadsheets are cumbersome, with traditional tools often feel like clunky black boxes, slow, outdated, and impossible to verify.
CalcBook is different. It's modern, intuitive, delivers professional hand calc style outputs that give engineers real confidence in the design.
Listeners of the Structural Engineering Podcast get 50% off their first 3 months. Just visit calcbook.com. Use promo code SEPOD. That's SEPOD.
CalcBook, built by engineers for engineers.
Interesting story. Very few people know this, but I'll share it with you. This same client, which is a company called Wright Runstead, they're a developer in Seattle. They were the same client who trusted us and let us do the first performance-based seismic design ever in the United States.
Wow.
So, we're 2 for 2 with these folks. They're very trusting and confident and believe that we have some chops and can do what we say we're going to do. So they hired us, and we did the very first performance-based seismic design. It was a building in Bellevue, Washington. Then it was called 3 Bellevue Center. Now it's called Key Tower, I think. But that was Wright Runstead as the developer, and that's who agreed to and allowed us to do the first performance-based seismic design project. That was in about 2000, maybe the late 90s even. And then they were the first one to, take the risk with us on Speed Corp.
Why is seismic sort of the leading place for performance-based design? Just curious.
Well, yeah, that's a good question. Why is it? Well, seismic is a particularly demanding load case or demand, right? It's a particularly challenging thing to design for. There are an excruciating number of prescriptive code provisions that force you into a very limited box. In particular, the R factors that are, when you go in the code, right, there's a table that lists the R factors, the response modification factors for these various systems. And if your system is not in that table, many believe it's not possible. And so the question really was, well, how do you unlock that door? And you unlock that door by using an alternative design methodology, which is performance-based design. And then you take the whole table with the R factors and the omega zeros, and you say, oh, that's a nice suggestion, but we're going to ignore it. And that's where you go. Now, so for me personally, that seed was planted in my brain in graduate school in a class that I took from Professor Bertero at Berkeley. And the name of the class was Limit States Design. And it was before we called things performance-based seismic design. That's where its roots are, right? Fundamentally, you're basically designing your structure to achieve certain performance under certain demand levels. In other words, certain limit states. And that was this whole class that Bertero taught on limit states design. And that was the seed that planted in my brain that ultimately became performance-based design that we know today. It's the outgrowth of that.
And there's more than just seismic at this point, right? There's a somewhat of a early standard for winds.
There's wind and there's fire, and coming soon is flood. But yeah, so seismic design we've been doing for 30-ish years, starting in the mid-90s. Yeah, starting about 1995, we started doing performance-based seismic design. Performance-based wind design, we hatched this idea maybe less than 10 years ago, probably more than 5 years ago. So it's pretty comparatively early days. And the idea on performance-based wind design, again, here's one of these things that you just trip across when you're like walking down the street. The thought that came to my brain was, well, there were two things that happened. One was on Rainier Square, back to Rainier Square. Oddly, Rainier Square design, the strength of Rainier Square is controlled by wind and not seismic, even though it's in Seattle. It's a tall, skinny building with a really aerodynamically poor shape. And so there was a very large dynamic wind amplification and demand on the building. So that, for example, the overturning moment for wind is about twice the overturning moment for seismic code level loads. So we had to, for the design of Rainier Square, we had to make the wind design compliant. So to be compliant with those demands, we had to make the building twice as strong as it needed to be for otherwise seismic demands, which goes 100% contrary to the philosophy of seismic design of wanting the building to absorb the energy and have some ductility and manage shear demands and manage foundation demands, etc., through absorbing the seismic energy.
Mhm.
And so that was kind of planted the seed of frustration, like, this is not right. And then the thought went further in my brain, which was, well, wait a minute. Philosophically, from the beginning of seismic design, that was the philosophy. We're going to absorb the energy from the maximum earthquake, allow some modest and perhaps even more significant amount of damage, but we're going to design against collapse. Yet today, still in the building code prescriptive provisions, under the maximum wind event, we still must design elastically, which to me, they're both natural hazards. Why in one case are we allowing the building to respond nonlinearly? In the other case, a different natural hazard, we say, oh, no, 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 not in wind. Doesn't make any sense. So then those two kind of collided for me and said, aha, that's it. We got to let our buildings breathe a little bit under extreme wind events and let them respond nonlinearly in a controlled, thoughtful, modest sort of way. Maybe not as extreme as we'll allow for in seismic design, but even just a little will be huge.
Yeah.
And so that's kind of how we got there. And so we launched this idea of performance-based wind design, like I said, more than 5 years ago, but not quite 10. To this moment, we've only built one building in the U.S. with that methodology. It's in Austin, Texas. It's completed. We're currently designing a few more. But like performance-based seismic design, it started with one, and then there were two, and then there were four, and then there were 8, and then there were 16, and then the ball rolls. And we're on that same trajectory, and it's just early days.
Give me a
Further on that,
I was
go
thinking
ahead.
performance-based fire. I really can't picture like what that is.
Yeah, so the best way to think about it is think about it in the here. Structural engineers will appreciate this. You built your ETABS model, and now you're going to run your ETABS model for the wind load, and you're going to run your ETABS model for the seismic load. I want you to run your ETABS model for the thermal load. And I want to understand how the entire building responds, your system responds to the heat gain from the fire and then the heat cooling period of the fire after it cools down. And how does your building, your structure respond to that load case? That's essentially what performance-based fire design seeks to do, is to mathematically, rigorously interrogate your structure considering real fire scenarios, just like we mathematically try to rigorously interrogate our structure for seismic ground motion demand. for windstorm demand. We're going to create load cases for real fire scenarios, and we're going to evaluate our design using those scenarios, as opposed to the code says I need a 3-hour separation, and that requires 1.5 inch spray-on monocoat done. My fire design is complete. Whether or not you achieved a 3-hour rating or not, you don't ever even really know. You just said, well, the code said I did, so I must. Just like the code says if you design your building for a seismic load and you use R of 8 for a moment frame, you must be okay. Yeah, you're all done. You're good. But you don't really know because you never checked. And that's the same thing with fire design. We don't check. To this day, no one checks how the building really performs under the fire unless you go through this more rigorous process. So that's it. So the end result of that, if you so chose to go that route, are a couple of things. One is you understand the performance of the building more clearly, so you might be able to improve the design and the performance of the design. And in doing so, you may be able to reduce or minimize or eliminate the spray-on fireproofing or intumescent paint on certain parts and pieces that you just show, I don't even need it, so I'm not going to put it. Whereas in other places, you might find, oh, not only do I need it, I need more than I thought I did. So it allows you to kind of allocate the protection in this case in a informed fashion as opposed to kind of one-size-fits-all fashion.
And you had already mentioned trying not to be just code officers, and everything you're saying right now is really sticking in my head is when we say we need 1.5 inches of spray fireproofing and done. We have an RV done. I wonder, how do we, just circling back, how do we push the profession, everyone in the profession, how do we move this to closer to performance-based, but also just the logic and thought into the product that we need to deliver, not just checking it.
Yeah, it's a challenge for sure. And I don't know that I know that I don't have yet the winning strategy to do that. But I agree with you that improving the state of practice, getting back to doing engineering as opposed to simply complying with the code, would be a really good and healthy thing. Part of it, I think, is demystifying and educating the profession about what this really is. Because I think with regards to performance-based design, I think there's a perception that, only the big sophisticated firms do that and the rest of us don't because it's too hard and it takes too long. And oh, by the way, we don't get paid nearly enough money to do that. And there's a lot of truth to all of that, I suppose. And so that's the kind of problem statement that we got to work on. And I wish I had the silver bullet to solve that problem, but we got to work toward that end. And part of it's education and demystifying. Another part of it is going to be, shall we say, standardizing third-party review. And I think it's a very healthy thing. It would be good for the profession to have third-party review of most things. But that said, also there needs to be some standardization and boundaries put on that review, because too often these days what we see and hear about and experience ourselves is when you get in those situations, the peer reviewers come in there with an agenda of their own. And they're going to show you how smart they are and how you did it all wrong and they're right, and you must comply with now their new rules that they're just making up as they go. And that's a problem. So there needs to somehow be some boundaries or at least guidelines put on the appropriate behavior and the appropriate scope and the appropriate approach to peer review. Instead of like, I'm going to show you how smart I am and how dumb you are, the better attitude would be, I'm going to help you make your design better. Your design's good, and working together, we're going to together make it better. That's like a great attitude of a peer reviewer, as opposed to too often it's like, no, I'm going to show you how smart I am, and I'm smarter than you, which is a bad way to go about your business.
That is just in our industry.
Mm-hmm.
Yeah.
Yeah. You really want it to be that everyone is working so hard to make it work.
Mm-hmm.
You know,
Yep.
everyone on the team wants it to work no matter what.
Yeah, ideally, that's the case. Not always turns out that way, though. So,
Max and I were talking the other day to a professor who used to be a professor, and he was telling us some of the challenges with education right now, specifically to a lot of universities that are having engineers or students in general taking less classes just due to the cost, as well as not requiring standardized testing like the ACT or SATs to do that. And one of his recommendations to our audience was, as new staff come on board, you've really got to make sure you understand what they know, because education is changing from when many of us went to school. And I think I've even seen that of talking to engineers that started in the 60s and 70s. They could just sit down, do all their work by hand. They knew the ins and outs of first principles and truly physics. And now there's so much reliance on computers. It almost seems like that may hold us back too from innovating, because people may not understand those basics of engineering to the same extent that they did back in the day.
Yeah, for sure. I see that 100% with the young folks that we hire out of school these days. We're faced with almost retraining them to some degree, because they're coming to us with, shall we say, the skill sets that are have some gaps, have some things missing. Yeah. So yeah, it is changing for sure. And AI ain't gonna fix it. AI is only gonna make it worse.
These audio issues. I started to ask an AI question, and I caught only the second half. Here.
How are you guys using it? What effects do you see? I don't know. There's too much of a question here, but answer whatever part you feel like.
Yeah. So to answer your question directly, we're not using it at all
Okay.
to do engineering. We are using it for data mining of historical information. We're using it for creating documents and reports. Word processing, it's like a fancy word processor that kind of helps write things on its own. But in terms of creating engineering designs, not at all. We are experimenting with a number of, I don't even know what you call it, because it's not software, right? They're not selling you software. They're more selling you service. And some of these services that are I'll call them quality control related, drawing review. We're experimenting with those a little bit to see if there's any value there. So we're tinkering around with it, but we're not using it to do our beam calculations, for example. Yeah. And where is it going? Well, who knows? I guess we'll see. I'm guess of the view that be a little facetious here just to make my point. But having AI do our beam calculations, I think, will be a flash in the pan, because we don't really need AI to do a beam calculation. I don't even need to do a calculation. I can tell you what size the beam is without doing a calculation. So the value proposition, the value offered by AI sizing beams or designing footings or things like that, I think will come and go very quickly. And we'll find out, that's not really what it should be doing. Where I do see significant value for structural engineers in particular is as a tool in the future where we'll be able to use AI in a way to more clearly communicate our design outcomes with our clients. So specifically, let's talk about it again in the context of performance-based design. And one of the kind of concepts of performance-based design is that for any hazard at any demand level, earthquake, wind, fire, flood, but you name the hazard and you name the demand levels that you want to consider, under those demand levels, I want to achieve certain performances. That's performance-based design in its essence, right? It's back to Burst Harrow's limit states design class. I'm going to define my demand. I'm going to define my acceptance criteria or my limit state, and then off I go. All right. So we have no means today to clearly communicate to our clients the design outcomes when we dial that performance up or dial it back down. There's a bunch of structural engineers very enthusiastic right now working on something called functional recovery and writing code provisions about functional recovery. A very noble pursuit, I think, and wholly in line with what performance-based design as a framework can deliver. In that regard, I'm like, yeah, very much behind it. But we have no clear way to define or to demonstrate or communicate to our clients what those outcomes really look like. I mean look like, physically, formally look like. And so my current hypotheses here, and I'm kind of keen on trying to figure this out, is if we were to be able to take our computer analysis outcome, marry that with a fragility database that informs damage states of everything from the plumbing systems to the drywall to the glass to the structure, and connect that to Hollywood quality special effects animation. And that's the AI that meshes that all together to where now I have science and math informing the Hollywood movie I'm going to show my client of his building, her building, under these different scenarios. Now I got something.
Yeah.
And I think that could be, if we can get there, that would be hugely powerful and very transformational in terms of how structural engineers are able to communicate with our clients about value that we can bring, design outcomes that we can achieve, and that gives them strength in their decision making on how much money they do or don't want to spend. That's a target I think we ought to be shooting at in the usage of AI, as to how to do that.
I wonder if it's foolishly optimistic of me to think that, if an AI platform can do the simple beam count, so I'm going to keep going back to my house version here. An AI platform can do every element of a house quite easily. And in 2 months, it'll be so quick. Could that push engineers to be more on the design in the sense of like speak with the architect, minor changes, like not just taking we finished our design, now make this a thing that will stand up in wind, but a little more conceptual and a little closer to the performance-based side that, beam check is so minor in every sense. But like, as we get more things that are minor, are we allowing ourselves to touch things that are outside of the old scope and a little more complicated?
Yeah, in a parallel alternative universe.
Yeah.
Not in the universe in which we live.
Shoot.
Unfortunately, I don't see that. Instead, my view is that it will further erode the profession's ability to actually innovate and conceptualize, because we'll lose touch with the numbers and the math and the science and the feel, right? And I try and counsel our young engineers here. with some modest success. But it's a conceptual thing, and that is when you're faced with a design task, before you calculate anything, before you turn on your computer, before you turn on your calculator, before you open your spreadsheet, draw me a picture of your design, draw a sketch, show me where the rebar goes, guess how much rebar should be there. How big is the wide flange beam? I don't know, draw it and guess. And once you've drawn a picture of your design, that's exactly your design. Now you can turn on your machines and run your math and confirm that you guessed correctly or not. And in finding out not, now you learn something. As opposed to immediately turning on your machine, it does whatever it does, spits out some numbers, and then you copy those numbers onto a drawing. And that's your design. And to me, that's really bad. Because you got no sense and no feel and you didn't design anything. You're kind of, you're a copy paste humanoid person. Yeah. It's not engineering. It's kind of clerical work. So anyway, I try and encourage folks to draw their designs first and think about how buildings go together and how pieces connect and how things should be. And if you're wrong, that's fine. That's what you learn when you turn your machine on and do your calculations. And then you'll guess better next time.
Yeah, I like that. When I was working out in the Northwest before moving to kind of more the Midwest, that's how I heard engineers talking a lot more is how is it going to act? What is it? Thinking of the building more at higher level even than jumping into the computer, being able to have that fundamental idea of how it's going to react to things and to that same point of what size things need to be. And I found as a get away from seismic country per se, or that part of the coast, that thought of those things kind of get away because like you'd mentioned in wind design, we don't allow anything to yield. So it's just and we apply a load and we design it and we move forward. So yeah, I like that a lot.
Well, I'm coming to town and I'm going to change that.
Perfect. I'm all for it. And then, AI being utilized to communicate. I mean, what a better, probably the best tool structural engineers or engineers in general need is a tool to communicate. So
yeah, for sure. Yeah, I mean, you see that in space right now with just a written word, right? Because structural engineers are notorious for being bad authors of things. And then we find, that the AI is very helpful there. It can help actually take engineers who can't form an English sentence and, turn it into something that the grammar teacher would be proud of. So,
yeah, isn't that the truth?
Mm-hmm.
Well, I think, those are the main things we really wanted to talk to you about today. One thing we find really fun to ask towards the end of the conversation is there anything that we haven't asked that you think would be really fun for our audience to know about?
So many things. If I just jump to one that it's a little bit of an advertisement, but sorry, you're going to have to. You didn't ask me. So, Ron, Speed Core, that's old news. Performance-based wind design, that's old news. What's next?
Yeah.
What are you doing now that, nobody really knows about, or and anyway, there's so many things.
Tell us all the secrets.
But the one that I want to talk about right now is this effort that we launched about a year ago now, and it has a name. It's called CURE. And CURE, CURE, stands for Code Updates for the Reduction of Embodied Carbon. And a report is going to be published in about a week. That's the result of a year-long effort to review the ASCE 7 code, ACI 318, and the AISC specification looking for all those provisions which, if they were recalibrated, reconsidered, would result in substantial reduction in embodied carbon. And this report's going to be published. They've found upwards of 100 code provisions. They've done to the trouble of prioritizing them in terms of bang for the buck, meaning here's an easy one, low-hanging fruit, won't take us much, won't be too hard to change, and it results in big changes in reduction in carbon. And so they've ranked them in this fashion. And then that list is kind of the roadmap for the next 5 to 10 years worth of research that we're going to do to go back and retool the entire building code.
Wow.
And so the simple example, just to give you a specific example of, well, what does that look like? The simplest one to get your head around is we're going to revisit the entire live load table and look at every value in the live load table and try and put some math and science behind the numbers that are there, because frankly, the numbers that are there, no one can tell you where they came from. There's not a living person on the planet Earth that can tell you where those numbers came from. In their kind of original, where did they come from, the chicken or the egg? I don't know.
Yeah.
So that's a simple example, but there's a lot of other, much more down in the weeds examples of things that we could talk about. That anyway. Yeah. So I'm giving this information to you to get the word out and to note that to live the dream here, to change all of these code provisions, it's going to be a very large scale effort involving lots and lots of different people, lots of researchers, academics, practitioners, code officials, etc., to put science behind these changes and then go and make the changes. So, and that's all forthcoming starting probably this fall.
Wow.
There'll be 5 to, probably closer to 10 years of research work to do to make all of these changes. And in the
those
end,
are pretty big codes.
Yeah. It'll be very impactful in the end of the day. Once again, the light bulb went on for me. It's like, we're always talking about, we can reduce embodied carbon if we use less steel. Yeah, I agree. Do a proper design and you'll use less steel. Well, more fundamentally is if we change the load or we change the load factor and we reduce it, now we've impacted every building in a positive way. And again, we're not trying to compromise safety here in any way. We're going to maintain, in fact, that's going to be part of the ambition, is to gain greater consistency throughout the code in terms of the reliability of the design outcomes. Because right now, when you get into the weeds, you'll discover there's a huge disparity in reliability and, to put it differently, safety as it relates to different demands and different design conditions. It's not consistent throughout the code. And so through this process, we aim to make that all more consistent and in alignment with the code's, shall we say, fundamental performance objective with regards to safety.
We've been talking with someone at NIST, I should say the name until we have the episode, but in September, we're going to shoot something with them. And I'm really excited to talk about. They look at the loading, the same thing that you were discussing, Phil. Maybe you would work together, or you do in this paper, but I am so detached from the reliability index of these loads and what we apply here. And I think it'll be really interesting to learn what we are actually using when we choose this live load and this wind speed and seismic current, different currents, and like.
Yep. Right now, as it's written in the code, it's very inconsistent across all of these things. In one case, you're achieving a very high degree of reliability. In other cases, not so much. Yeah. And so part of this effort will be to try and get greater consistency and alignment amongst all these different things. That's an outgrowth of just the fact that all these things get conjured up and cooked up in kind of isolation, right? They're all a byproduct of smoke-filled rooms and committee negotiations. So
Yeah, tremendously. The live loads connected with me. I was doing a taller mass timber building, and the discussion of taller CLT shear walls came up, and talked to one of the professors that did the research, because there's a 65-foot limit in the table in chapter 12 of ASC 7. And I started going down this deep dive of why is there height restrictions per system use, if you just stick strictly to code.
Mm-hmm.
As I started diving down that, the people I reached out to just kept saying, we're not really sure. We think people drove around after the last few earthquakes, marked the damage and how tall the building was and what system it was, came up with a height that felt comfortable, and we just put that in the code.
Chose 3 numbers and it applied to everything across the board, or with 4, but
there's some truth to that. The only one that I know of that is got some, I wouldn't even call it science, I'll call it pragmatism behind it, is there is a 85, is it 80 or 85? I don't know. I think it's 85-foot height limit. It relates to the height that the ladder on a fire truck reach.
that's a good one. Yeah.
And that's where that number comes from.
Huh.
It's the highest that the hook and ladder truck, when they bring the big truck with the ladder on the back and they put the big hydraulic thing up and then it goes up and it telescopes.
Mm-hmm.
The reach of that ladder set that 85-foot height limit. That's where that number comes from. It's
Wow.
from a firefighting practical limit. The rest of the numbers in the code, I got no idea. They all came out of the cosmic ether. I mean, I know a couple of them. We don't have enough time on this podcast to talk about the other numbers I know about, because they're hysterical. When you know that, when you go, really? Oh, I'll give you the punchline. The 240-foot height limit on shear wall buildings, which is 50% greater than the 160-foot height limit, comes from a shadow study in 1920 in downtown Los Angeles, talking about shadows of buildings cast on the sidewalks of downtown LA, that then was tried to be written into the building code as 150 feet, and it was a typo, so it became 160 feet. And then 160 feet became 240 feet as the result of a committee negotiation, thinking, we need to make it a bigger number than 160. So the 240 that's in the code today has its roots in a 1920 shadow study in LA, and it's further complicated by a typographical error in the 1958 version of the code. Yeah, so that's the beauty of 240. It's a typo based on a shadow.
So very logical that we're limited to those heights.
Has everything to do with math and science and structural engineering, right? Exactly. Well, that's the truth of it. So when you understand that, then you go, well, dang, if that's the case, what else is in the code that's all made up stuff like that? It's littered with stuff like that. So.
Yeah. Well, the next time I do a building that's only a few feet taller than those limits, I'm just going to put that in my calcs for the code reviewer to review and say,
you'll see what happens.
Don't worry about casting shadows on this one.
In your calculations, you just say, call Clemensic for a third-party review. I'll give you a passing grade. So, yeah.
Gosh,
So Cure, back to that, Cure. People should know about Cure and support that going forward, because it's kind of a thing.
Right. Well,
yeah. If people wanted to learn more, where could they find more information?
I think there's a website they created for Cure. There is. So you just Google Cure.
we'll put in a show notes also.
Carbon reduction. The primary financial sponsor of this effort is the Charles Pankow Foundation. So if you're interested in innovation, Cure, and a whole lot of other things in general, the Charles Pankow Foundation So pankofoundation.org, PANKOW, pankofoundation.org. You go on that website, and there's bundles of stuff there to read about and think about. And the Panko Foundation has funded everything from performance-based seismic design development to speed core to fast floor to wind design to fire design to embodied carbon reduction, and on and on and on and on. A lot of the funding to make all of that go came from the Panko Foundation. So go there and rummage around, and you'll discover all kinds of interesting new things.
That sounds great. Well, Ron, thank you so much for being on the podcast. I've learned a lot personally. I have a million questions about the code in the world and structural engineering that we'll have to find another time to talk more about, maybe at another conference or something.
Fair enough. Well, so I'm going to leave you with, the challenge that I offered you when we started this conversation is I need from you a recommendation for a song parody about structural engineers that could be a crowd rouser, right?
Yeah.
They want to take a song and change the words and have a bunch of structural engineers, to get them to sing along and participate and have a good time. What is that song? So that's your challenge. Come back to me with a good idea for a song.
Okay. And if Max and I come up with a good one, we will insert it right here.
This is my world, this is my arena. Every street, every bridge, every column and beam started with a question, started with an idea. Could we make it stand tall? Could it reach a little higher? Put the pencil down, pick the hard hat up. Learn the forces, learn the failures, learn when it's not enough. Everybody sees the building, everybody sees the art, but we see every pound from the roof to the foundation. I studied every great one, every failure, every frame. Learned that nothing built to last was ever made without the pain. The greats weren't great because they knew the kids at birth. The greats got great because they count a lot. We came to build. Look around, this is the proof. Every roof above you, every floor beneath your shoes. We came to build every road that takes you home, every bridge across the water, every tower made of stone. 4 years for the degree, then the PE. 4 more years becoming who you're supposed to be. And when you finally get the letters after your name, you realize the license wasn't the point of the game. You came to build. Look around, this is the proof. Every roof above you, every floor beneath your shoes, every stadium full of people, every hospital and tower. We don't just build buildings, we build the world around us. Most people never see it, never know what holds them up, because that's how it's supposed to be. We make it stand, we make it move, we make it lighter, we make it stronger. We came to build, look around, this is the proof. Every roof above you, every floor beneath your shoes. We came to build every road that takes you home, every bridge across the water, every tower made of stone. We test the idea, we change the math, we find a better way. And after all those years, all those nights, all those drawings, all those cabs, we came to build. Look around, this is the proof. Every roof above you, every floor beneath your shoes. We came to build. Every road that takes you home, every bridge across the water, every tower made of stone. You look around and realize you helped build this
Oh, wow. Well, I guess you can blame AI for the last 3 minutes.